Everyone, I'm Aindrila from the University of Calcutta, and today I'll be presenting on the topic electrochemical understanding of the difference between spherocyte suspension from normal discocytes for hemolytic anemia detection. The outline of my presentation will be as listed. It will start with a brief introduction to the disease at rest, followed by the experimental works and results obtained. Now, let us first have a look at why such a study is required. We are all familiar with the disease anemia. Almost 1/4 of a global population is suffering from it. A recent study published in the Lancet Hematology has reported that over 2 billion people are presently anemic across the globe, with most cases in sub-Saharan Africa and South Asia. The picture here in India is also very concerning. The National Family Health Survey reported that the number of anemic population, or the percentage of anemic population, has only increased over the years. Now, anemia is commonly described as a lack of blood or caused by dysfunctional RBCs. Today, we'll be focusing on spherocytosis leading to hemolytic anemia. On your right, you can see a normal RBC. It is discoid or biconcave in shape, and it includes hemoglobin, which has 4 heme structures. Each of these contain an iron center. This iron-containing protein is responsible for all the gaseous transports throughout our body. Now, in normal physiological conditions, this iron here is present in the Fe2+ or ferrous state, and it auto-oxidizes to the ferric or methemoglobin, that is Fe3+ state, and releases ROS, that is reactive oxygen species, as a byproduct. In spherocytosis, where the RBCs are unable to hold their normal shape and transforms into spheroids, such auto-oxidation is increased several times and uncompensated by the activity of methemoglobin reductase. The ferric hemoglobin there is a non-functional form of hemoglobin, and the body uses enzymes like methemoglobin reductase to reduce it back to the ferrous state. But such activities are affected due to spherocytosis, and it increases the amount of ROS produced in the body, leading to hemolysis or cell death, and hence the term hemolytic anemia. An early detection of such conditions can lead to better or improved treatment. Currently, traditional techniques like MCV and CBC are used to get blood profiles, but they require a minimum volume of at least 2 ml. Again, bone marrow examinations are very costly, and osmotic fragility test, or OFT, that measures the ability or the probability of blood cells to rupture, that too is time consuming. Moreover, none of these have been yet transformed into point of care devices, and they require expert technicians. In this regard, researchers are looking for better alternatives, and electrochemical techniques like cyclic voltammetry and EIS spectroscopy are providing advantages like rapidity and reduced sample volume and on-chip point of care detection. So we thought, why not explore the electrochemical properties of spherocytes to detect hemolytic anemia? And to do so, we first procured the blood from normal individuals as well as patients suffering from spherocytosis. Such heparinized blood was then centrifuged at around 9,000 RPM to separate the plasma, followed by PBS washes to obtain packed cells or isolate the red blood cells. Then we prepared different HCT percentages, that is hematocrit percentages, with packed cells and PBS by mixing them in volumes as listed in the table. The same images here show the morphologies. You can look at the first one, marked at A, the discocytes have a clear depression in their centers, while spherocytes lack them and are completely round or spherical in structure. And for all the electrochemical measurements, we've used a commercially available 3-electrode chip attached to a potentiostat, and the minimum volume that of the sample that we've used is 20 microliter. Now, first let us look at a few physiological aspects. Co-oxidation studies of isolated hemoglobin have been studied in the presence of NBT, that is nitroblue tetrachloride. Now, this enzyme enhances the oxidation, and the oxidation profile here shows that the formation of methemoglobin in spherocytes is highly increased with respect to discocytes. So at any time, the total amount of methemoglobin content in spherocytes is higher compared to that in normal discocytes. Again, from Raman spectroscopy, we can observe that the 1637 centimeter inverse peak, which characterizes the oxygen concentration, is reduced in spherocytes, as well as the peaks at 1563 and 1587 centimeter inverse respectively, marking the oxygenation state of hemoglobin, are also reduced in spherocytes, meaning that most of this hemoglobin present in spherocytes are in deoxygenated state. Thus, we can see that in normal, if we take two cells, a discocyte and a spherocyte will have a higher content of methemoglobin and a lower affinity for oxygen. Now, from cyclic photometry studies, CV we know explores the redox activities of different species. In our case, it is the ferrous hemoglobin oxidizing into the ferric. Now, we've observed the oxidation currents for both the cases with a potential sweep, and it is quite evident from the graph that the oxidation current is reduced in spherocytes as compared to discocytes. Now, such current originates from the transformation of ferrous ions into ferric by releasing an electron at the working electrode. Now, as discussed in the last slide, spherocytes contain a larger amount of methemoglobin, and hence the ferrous ions undergoing such oxidation is much reduced, leading to a lower oxidation current here. Moreover, from the differential curve there, you can also observe that in addition to a lower oxidation rate, spherocytes also require a higher potential to attain such maximum oxidation rate. We have attributed this to the reduced surface to volume ratio of spherocytes. Moving on to the EIS analysis. From the plot on the left, you can see that with increasing hematocrit percentage, that is the volume of RBCs in solution, we can observe the impedance to be increasing both for discocytes as well as spherocytes. Now, this is because in the total solution, the amount of ionic volume, that is PBS, is gradually decreasing as we keep on increasing the HCT percentage. And there are previous reports also, we have observed the same or similar trends. They have tried to use EIS to quantify the cells in such solutions. What is interesting to note here is that for every HCT percentage, spherocytes display higher impedance compared to discocytes. Now, this can arise due to their morphologies. In case the discocytes here have been reported to have proper or good dielectric bodies with dipoles randomly oriented in the solution. Once we apply a field, such dipoles are readily aligned, posing a low resistance to the flow of current. While in case of spherocytes, due to their spherical symmetry of ion distribution, they have weak dielectricity, and the field applied must first create proper charge displacement and alignment, and hence the effective electric field driving the current through the solution is diminished. Therefore, a higher impedance is obtained for spherocyte solutions compared to discocytes. Thus, in conclusion, we can see that spherocytes demonstrate a lower oxidation rate and compared to that of discocytes, and they have also been corroborated with the co-oxidation and Raman studies. Moreover, EIS reveals higher impedance in case of spherocytes compared to that of discocytes due to their weak dielectricity. So, determination of such EIS responses as well as CV-derived oxidation rates can provide a potential method for a rapid and cost-effective diagnosis of hemolytic anemia due to spherocytosis in the body. Here are the references. I'm thankful to everyone listed here and the audience for your patience. Thank you.